So we can start now.
Yeah, I'll just introduce you quickly.
Yeah, sure.
It doesn't come up on my screen. Hopefully everyone else's screen. Okay, welcome everybody to this month's Fleet Seminar, or one of two for this month, actually. And today we have Patjaree from RMIT. Patjaree has just finished her PhD not that long ago with Torben, one of the fleet CIOs at RMIT, and we can announce exclusive announcement that he's just taken on a role at CSIRO. So congratulations, Patjaree. But a little potted history of her time at Fleet. She was selected. She's done a bit apart from finishing a PhD. She's received some Fleet funding for a Women and Leadership Impact Program, and at the moment she's working on a project that she received a Fleet translation funding for, to extend the LED device lifetime with a liquid metal printed oxide. So that relates quite well to her talk on liquid metals. So I'll hand it over to Patjaree now to run the seminar.
Thank you for the introduction, Jason. So, hi everyone. My name is Patjaree, and as Jason said, I recently graduated from RMIT University. I'm very happy to be here today to talk about the tutorial review that we published last year within our group, which is the liquid metals, an ideal platform for the synthesis of two-dimensional materials. And I would like to acknowledge these people who have helped me in writing this tutorial review. Some faces are familiar, I guess. And yeah, let's get started. So as the topic said, it's about liquid metals, the platform for making 2D materials. Right now, the title may seem like a lot to process, so I might just break it down to a few keywords and introduce you to what we are doing here. So the first one I would like to talk about is the synthesis of two-dimensional materials. So as everyone knows that these days you've got a bunch of techniques when you want to synthesize 2D materials. You've got a top-down approaches, including, for example, mechanical exfoliation or the Scotch tape technique, the liquid exfoliation, the etching, and you also have bottom-up approaches such as chemical vapor deposition, physical vapor deposition, wet chemical preparation, and so on. Of course, these techniques are well developed, well known, and now widely used these days, but still there are some challenges that should be addressed, and we should look into that, be it high cost, high processing temperature, and complexity of the system. So how about we can come up with the alternative way to make 2D materials that is cheaper, can work at relatively low temperature, simple, but also effective in the results. And this is where I'm going to introduce a role of liquid metals. So we identify liquid metal as a metal and alloys at the liquid form at relatively low temperature, about 350-400 degrees C. Actually, both core and interface of the liquid metals can be exploited in many applications, but the latter part, which is the interface of the liquid metals and alloys, plays a key role into the material synthesis. So we will focus on this one. So the liquid metals, when exposed to oxygen environments, surface oxidation can occur simultaneously, which can be described by the Cabrera-Mott oxidation theory. So the way they described this was electrons from the metal tunneled through the growing oxide layer, resulting in the self-generated electric field called Mott field. And this field promotes the diffusion of metal and oxygen ions into the oxide skin, and that leads the oxide to grow. And as the oxide becomes thicker and thicker, the strength reduces until ion diffusion is depleted. or in another word, this process is self-limited. So this is the oxide growth at the surface of liquid metals. So according to this model, it means that, for example, if I take gallium, melt it, and expose it to the oxygen environment, I would expect to see gallium oxide at the surface. And this would be applied to, for example, indium and bismuth, where I can get indium oxide and bismuth oxide at the surface, respectively. However, if we alloy two different metals together, this cannot give us an access to a variety of 2D materials, because alloying can help suppress the melting point of the system. So one good thing is the liquid metals with the low melting points, such as gallium, can act as solvents to the metals that have higher melting point temperature. But there's some key factors that need to be taken into account when you want to making an alloy. So according to the Hume-Rothery rules, the solubility of two metals within each other would be high if these two metals have similar atomic diameters, similar crystal structures, same valency, and similar electronegativity. So this might be the thing that we have to consider. And the way we fabricate the alloy would be very simple method, like mechanical grinding using mortar and pestle to remove the pre-existing oxide skins, and also help to mix the two metals together to get the homogeneous alloy. And we usually do this in the inert atmosphere, such as glove box. So the way we know which oxide of the two metals will form at the surface, we have to look at the Gibbs free energy of formation. So the one that has the lowest delta GF will form preferentially and simultaneously. So if you are interested in predictive equation theory, you could check out this paper from Abigail Goff, an exploration into 2D metal oxides and other 2D materials synthesized via liquid metal printing and transfer techniques. So now we are going to talk about the methods that we have developed from the liquid metal to get to the oxides. So as I mentioned, the oxide skin that is formed at the surface of liquid metal is weakly attached to the parent liquid metal. And this results in easy exfoliation of this oxide skin onto other desirable substrate. So several methods have been developed and can be mainly divided into dry and wet synthesis. So I'll briefly review some of these methods throughout the talk here. So the first one I want to talk about is the touch printing method. So this one is very simple. So all you need is just a substrate that you put the liquid metal on top of that. And then you need another substrate to just gently touch a liquid metal. So this is how it looks like. So you can start by heating the metal to its melting point and then touch the surface of the liquid metal with a preheated substrate. Then the oxide skin will be transferred onto another substrate. The right images here shows 2D bismuth oxide that is obtained from the liquid bismuth from the touch printing method. And at the bottom, you can see 2D antimony oxide obtained from bismuth antimony alloy. And in this case, we got antimony oxide because the Gibbs free energy of formation of the antimony oxide is lower than bismuth oxide. Another one is the squeeze printing method. So this one is starting off very similar to the touch printing. So this one requires two substrates. So starting off similarly to touch printing. So the metal is placed on one substrate and then heat to its melting point. Another substrate is then brought into contact to squeeze downward gently, resulting into the oxide layer that attached to both substrates. And this technique is employed to synthesize 2D ITO from indium tin alloy and 2D gallium oxide from the liquid gallium. Next one is the role transfer method. So this one just imitate the movement of handwriting, but instead of using a pen or pencil, you are using glass pipette to drag the liquid metal across the surface of the substrate. And we have used this technique to synthesize 2D p-type beta tellurium oxide from liquid selenium and tellurium alloy. And we have shown here that this technique can be employed to synthesize this material onto a variety of substrates and can do the multi-print, which result in bilayer tellurium oxide as well. So in some applications such as catalysis or reinforcing polymer fillers, you might want large quantities of nanomaterials in liquid suspension that can be further processed later. So we have introduced one of the wet method here, which is bubbling method. So the way it works is the pressurized air is injected into the liquid metal pool submerged in a silex solution, creating air bubbles in which metal oxide is formed at the bubble surface. And then these oxides accumulate in this solution, and you can collect this, do the drop cast, and can be further processed. So these are examples of the materials that we got from the bubbling method. So we got gallium oxide and hafnium oxide. So we not only 2D oxides can be obtained with these techniques, but also the materials like with other compounds as well. So the way we can synthesize these 2D compounds is the first one would be altering the reaction environment. So as shown here, we have synthesized tin sulfide from liquid tin in the presence of H2S gas, like instead of oxygen environments. Another way to do that is post-processing. So you synthesize 2D oxide and then you further process it by, the first one is vapor phase anion exchange. So this one, the reaction involves the anion exchange and the removal of oxygen species via the vapor phase, so similar to CVD. It is also recommended that the obtained 2D materials, like in this case gallium nitride, are kept in inert environments after the synthesis to prolong and to avoid the reoxidation. The second post-growth processing that you can have a look is a solution-based method. So the solution-based method has been investigated here, where indium oxide was converted into indium oxysulfide. So the 2D indium oxide sheets were immersed in the trisulfur radical anion, which enables sulfur insertion into the indium oxide, resulting in partial oxide anion replacement at relatively mild condition. Even the complete sulfurization wasn't achieved. The metal oxysulfides are increasingly being studied for electronic applications and catalysis. So once we get those 2D materials, we can also integrate them, like stacking them on top of each other to fabricate the heterostructures system. That can be further used for advanced electronic applications. So a lot of assembly techniques have been established and studied, including direct synthesis and also deterministic transfer methods. So the first one is the direct synthesis method, where showing here is we create the tin oxide monolayer first with the touch printing, and then we do the touch printing again, but on indium metal. So we get indium oxide on top of the tin oxide. Sorry, it should be tin monoxide. And interestingly, with this transfer method, we observe the presence of van der Waals gap between the two layers. I've got another example here, which is this is a cross-sectional TEM of monolayer ITO from squeeze printing. So you can see here that the layer of the ITO is about 1.4 nanometers. While if we do the squeeze printing again to get bilayer ITO, you can see here that we've got around 1.5 nanometer of van der Waals gap, which is interesting. So another way to do the transfer apart from the direct synthesis is called the deterministic transfer method. So this technique was developed and was published in Matthias papers. Okay. So to work on this method, you would need a transfer stage equipped with a microscope and the heating cooling system, and also PPC and PDM as polymer stamp to help with the transfer. The way it works is first the polypropylene carbonate or the PPC, which will be used as a sacrificial layer, will be spin coated on top of the elastomer stem made from PDMS. Then the gallium oxide will be directly synthesized on top of this stem through the squeeze printing technique at about 40 degrees C, which is above its melting point, before getting cleaned with a UV ozone treatment, but this part is actually optional. After that, it will be aligned with the other 2D materials on another substrate, utilizing an optical microscope that attached to the transfer stage. And once bringing them in contact, the stage will be heated up to 120 degrees C to completely release the PPC layer that has gallium oxide sheet on top. And then this temperature will be held for roughly 1 minute to completely soften the PPC and make sure that gallium oxide is fully transferred onto the desired area. And then once we bring this stage down, we kind of like separate the stem from these structures. So the next step would be get rid of the PPC residue that would still be left on top of the substrate by cleaning with acetone, IPA, and ethanol respectively. And this is the result that we are after. Interestingly, after doing the transfer, after 2D gallium oxide was transferred onto another substrate, we also observe again the increased step height, which would be a result of the presence of van der Waals gap. It actually shows that despite of the non-stratified nature of the gallium oxide, it can maintain 2D characteristic when being transferred and stacked. So you can see here that originally the gallium oxide after synthesis, like direct synthesis on substrate, the height would be around 3 nanometer, but after the transfer, the height increased to 6 nanometer, and this is a result of the van der Waals gap that we were talking about. So in terms of the applications of the 2D materials from liquid metals, we can use them for example, field effect transistor. So showing here, we have N-type semiconducting oxide, P-type semiconducting oxide, and also it can be used as dielectric oxide material as well. So this is actually very interesting. So especially 2D gallium oxide can be used as a protective layer. So this one is the work from Matthias, which was published 2 years ago. So this work has demonstrated that an encapsulation of tungsten disulfide with ultrathin gallium oxide synthesized from liquid gallium can be protected. So you can see here in figure A and B here that it not only protects the tungsten disulfide, it can enhance the optical property of the materials as well. And also it protects the tungsten disulfide from further fabrication process. So if you look at the picture E here, you can see that the top one is tungsten disulfide being capped with HBN, and then Al2O3 was then deposited with the conventional vapor phase deposition. And the result here, you can see that the intensity of this one is here, the green one of the one that's capped with HBN. But when we capped it with the gallium oxide instead of HBN and then do deposit another Al2O3 on top, you can see that the intensity is higher. So that's kind of proof that gallium oxide is working effectively in being a protective layer and also enhance the optical properties. Another work that we did in collaboration with QUT is we used 2D gallium oxide as a dielectric layer for H-diamond MOSFETs. So in this work, we used 2 layers of gallium oxide as a gate oxide layer for H-terminated diamond MOSFET. And the material was synthesized through a squeeze printing and then transferred onto the diamond device with a deterministic transfer. And the whole process was repeated to print another layer of gallium oxide on the device as well. So this is the AFM of the structure. And we can see again the van der Waals gap that's present between 2 layers here. So we characterized the device and we found that the effective dielectric constant of the gallium oxide is about 3.6, which is comparable to SiO2. And we also do the long-term stability test to see the output curves, and we observe no degradation after 1 month exposure in atmosphere. So from this work, and I know that there are other groups that are doing use gallium oxide as the gate oxide layers as well. So this kind of proves that it has the potential to be an alternative of HBN, which might have limitation in size. Another applications that we could look at is the photo detection here, where the first row you can see that is actually the indium oxide and tin monoxide heterostructures that we talked about in the previous slide. It's also got other applications as well, which is capacitive touch screen. This one is ITO. Gas sensor. This one is gallium sulfide, which was synthesized by the post-growth processing. And this one is some memory stuff from 2D tin oxide and a lot more that I wouldn't talk about in this talk. So the key takeaways of this talk would be liquid metal-based synthesis technique have been developed in recent years and can help address some challenges when it comes to synthesis of 2D materials, be it the lateral size, substrate mismatch, and also the inconsistent layer thickness. So these methods allowed a bunch of 2D materials to be explored, especially non-stratified materials that would be challenging to obtain via the conventional methods. And not only just the oxide materials, we can have access to 2D compound system as well, like nitride, sulfide, and so on. This can be synthesized by altering the process, altering its environment, or also post-growth processing. The obtained materials can also be stacked on top of each other to fabricate heterostructures, and this is very helpful and useful to access the advanced applications. And in terms of future work, I think we should look and aim to study more complex alloy systems and the mixed oxides, because the predictive equation that I mentioned in Abby's work, that one is now only work with the binary alloy system. So if you want to look at the tertiary alloy systems or oxide, we have to further develop more fundamental knowledge on this. And future work also should focus on exploring different 2D materials, especially the one that haven't been synthesized before with the conventional method. Also, in terms of the post-growth processing, we can probably look at chemical intercalation, since we already know that the van der Waals gap exists between two layers when doing transfer. And also, researchers might be look and develop more fundamental knowledge in the surface chemistry and physics that's happening at surface of liquid metals and alloys. And also, wider range of transfer techniques should be looked at so that we can work at different temperatures, because right now we are using PPC, which has very low melting point. So we can kind of only make gallium oxide on top of the PPC layer. So if we can find alternative sacrificial polymer that can work at higher different temperature, like we can probably look at that. I think I've finished really. I've got a bunch of time left, but I would like to acknowledge my supervisors, which are Associate Professor Torben Denneke, Dr. Aaron Elben, and Professor Chris McConville for supporting me throughout my PhD. Also, Dr. Alice Labady, Dr. Nitu, all of my PhD colleagues, collaborators from Fleet and non-Fleet, and also facility at RMIT include MNRF and RMMF. And thank you for your attention. I'm happy to take questions if there are any.
All right, guys. Thanks, Patjaree. But yeah, just unmute yourself, guys, and ask the question, or if you want, you can put it in the chat. Sorry, guys, hang on 2 seconds. Sorry, if guys, if there's no questions, we might thank Patjaree for the seminar. And good luck, Patjaree, on your new big adventure.
Thank you. Thanks, Jason. Thanks, everyone.
Okay, bye.
See ya.
Patjaree, just before you disappear, actually, can I ask one question?
Oh yeah, sure. Yep. Sorry.
You showed some results on putting a dielectric on top of hydrogen terminated diamond.
Yes. Yep.
But I didn't grab a reference. I couldn't see a reference for that.
The reference.
Have you got that slide again you can share?
Oh yeah, sure. Got it here. 1 second. Let me. Just 1 second.
Right. Share your screen again, Patjaree. Yeah, that's the one.
Can you see this screen?
Yes.
Yeah, I put the reference very small here.
Okay, so this is gallium oxide on top of
H-terminated MOSFET. Yep.
Bottom left,
Okay.
Alex, down the, you'll see the.
Yeah, bottom.
Oh, right down the bottom.
Yep,
Sorry, my eyes are too old.
That's so sorry. I should put it up top, maybe.
Yeah, no, it's just right. Okay, now I've got it. Do you know what the mobility looked like?
The mobility, I think we can just do this. I think it was 45, which it's kind of okay for edge-terminated diamond. So the main aim of this paper was to demonstrate that we can use gallium oxide as protective layer and dielectric layer. So we didn't aim to make the best performance edge-terminated diamond. So yeah, but we can have a look into that and further improve that, maybe increase the number of layers of gallium oxide that we use, things like that.
But already how thick is 2 layers of gallium oxide?
So it's here about 6.73.
Okay.
It is shown in the AFM here. Yep.
And you've got a voltage range of 2 volts.
Yep.
That's not too bad.
Yep.
Do you know what limits going even higher in voltage?
I'm actually entirely not sure, because so this work was I did its work with Kaijun Singh, and he actually did the measurements. So I think he might be the best person to talk to in terms of the measurement of the devices. Yeah.
All right, that's great. Thank you. That's really nice. Oh,
thank you.
Actually, do you know, so when you put the 2 layers down, do you know how, when you've only got 2 layers, it's going to matter for the device uniformity that the 2 layers are 2 layers plus or minus 0 layers, not 2 layers plus or minus 1 layer.
Yep,
right?
yep.
So do you know how uniform that 2 layers is, like across the device?
Across the device. So I think it's quite uniform. So because the way we made it is like we did the transfer technique, right? So we firstly print the gallium oxide onto the stem first, and then I have to look at the stem, like look at the gallium oxide on the stem and select the good area, like the homogeneous area that to be put on top of the devices. Yeah, but it could be like some crack or something happening. But usually, gallium oxide is very homogeneous.
Mm-hmm.
And yeah, with our method, we demonstrated in other paper and other work that it's a quite large and homogeneous scale. Yeah.
So over a 10 micron by 100 micron, would I expect to have?
Yeah, it could be for gallium oxide, depending on the method that you use to create it, it could be up to millimeters. It's very, yeah, it's very
cool. Good. All right, I will dig that paper up and have a closer look. Thank you. That's really nice.
Thanks.
All right.